Hello, my name is Nigel Bowden. I'd like to welcome you to episode 16 of the Wi-Fi for Beginners podcast. This is a series of podcasts discussing the fundamentals of wireless LAN networking. In each episode, we'll take a look at a different aspect of Wi-Fi to build your understanding and knowledge of wireless LAN networks. Each episode is accompanied by a set of slides describing the topics covered in that episode, and although you don't need to review these slides whilst listening to the podcast, they will be useful for review material we discuss and might provide some visual aids to help you more fully understand some of the concepts and equipment described. All recordings and supporting material for the podcast series can be found at wififorbeginners.com. If this is your first time of listening to the podcast, I'd like to welcome you along. We're currently discussing wireless LAN clients. The podcast series is broken down into a series of major wireless LAN topics, and back in episode 13 we started talking about wireless LAN clients, a very important topic within a Wi-Fi networking world. If you'd like to review some of the previous modules that we've discussed, I suggest to go back to episode 1 and work your way through the episodes in sequence as we cover a whole series of topics, and the knowledge that we acquire at each stage builds from episode to episode. So as we're already up to episode 16, it's well worth going back to some of the older episodes and reviewing some of the material there. So in episode 15, we were actually talking about 802.11 frame types, which are used by wireless LAN clients and wireless LAN access points. If you're following along with the slide deck, we actually covered slides number 25 to 30, and I'll just do a very quick review of those before we dive into some new material on this particular episode. So we had a look in slide number 25 at why we actually need different types of frames for wireless LAN networks. We talked about the fact that in Ethernet networks we only have one frame type at layer 2. Obviously we're talking about layers 1 and 2 in the OSI stack here, and at layer 2 we've only got one type of frame in the Ethernet standard. In wireless LANs we have 3 frame types, and this is due to the fact that wireless LANs operate on an unbounded medium compared to Ethernet, which operates on a bounded cable medium, and so this means that we've got access and contention for the RF medium that the wireless LAN networks operate over quite a wide physical area. So this presents us with quite a few problems compared to Ethernet in terms of restricting access and controlling access. And with the wireless network, we don't have the same simplistic access method that we have for an Ethernet network. With an Ethernet network, we can simply take our data cable, plug it into a data port on the wall, and instantly get a full duplex uncontended connection that we can send data over. And then as we move into other rooms, we can simply plug into new data ports in each room. With wireless LAN networks, we don't have that luxury, and we have to try to emulate that behavior through the use of these 3 different frame types that we're just going to quickly review now. So the first type of frame we're going to talk about is management frames, and management frames are used to discover wireless networks, to join a wireless network, and to leave a wireless network. This is very much analogous to plugging in and out of a switch port on an Ethernet network. Within the management frame type, we've got a number of subtypes. For discovering networks, we've got beacon and probe frames. For joining networks, we've got association and reassociation frames. And to leave a network, we've got disassociation frames. And these are just a few examples of the different subtypes of management frames that we've got. There are plenty of others as well, but these are some of the main types that you may come across in your initial studies of wireless LAN networks. The next type of frame we talked about were control frames, and these are used to assist with the delivery of data frames. And examples of subtypes of this particular frame are acknowledgement frames, block acknowledgement frames, and RTS and CTS frames. And then the third and final frame type that we talked about were data frames. And these are the frames which actually carry the user data, which is transported end to end using layers 3 to 7 of the OSI stack. And again, we have a number of subtypes of data frames. We have a simple data frame, we have quasi data frames, and another data frame subtype you may hear of is the null data frame. We also discussed the fact that data frames are the only frame type which is responsible for delivering user data. So in this context, in terms of user throughput, all other frame types can actually be considered as protocol overhead because they don't actually directly deliver any user data themselves. And finally, we spoke again about client roaming. We've mentioned it a few times in previous episodes of the podcast. It's a very important process that we need to understand. And we highlighted the fact that client roaming decisions are actually purely a function of wireless clients. It's not actually the wireless infrastructure, the wireless access points or the wireless controllers which are responsible for deciding when a wireless client will roam between access points. It is purely a decision that's made by the wireless client itself. And there are a number of criteria that a client may use to make the decision to roam. Primarily, it's going to be things like the received signal level of the access point that it's currently associated to, but there may also be factors such as the current connection speed and error rates, things like that, which may influence whether or not a client decides to make a roaming decision. And the other key piece of information is there is actually no standardization around the client roaming decision within the 802.11 standard. It is all very much vendor specific, and each vendor will implement its own roaming algorithm, which it very often doesn't publish the details of. So it's very difficult to predict the roaming behavior of many wireless LAN clients. So if you're following along with the slides, we're actually now on slide number 31, and in our discussion of wireless LAN clients, the next thing we're going to take a look at is client speeds. When we're considering a wireless LAN client, what are the factors which affect the speed at which it will connect to our wireless LAN infrastructure? And there are a number of factors that we need to take a look at. The first one we're going to talk about is the quality of the RF link between the wireless LAN client and the wireless access point that it's actually communicating with. There are a number of factors which affect the quality of the radio frequency link between the client and access point. First one is the signal level. Is the wireless LAN client receiving its signals from the wireless access point at a reasonably high level so that it can easily decode the data that's being sent from the access point to the client? We also have to consider errors, as we do on a wired network. If we've got too many errors, then certainly the quality of the link between our client and access point is going to drop. So we certainly want to minimize errors over the RF link. And also a very important one is noise. We can have noise from sources such as other wireless LAN networks which are in the vicinity. We can also have noise from non-Wi-Fi interference sources, things like microwave ovens and baby monitors, security cameras and other devices which use the same bands as wireless LAN networks, and these can all add to the noise floor that our wireless LAN client experiences, and this can degrade the quality of the RF link between the client and access point and reduce the speeds which can be achieved. In addition to these environmental type factors which are going to affect the RF quality of the link between the client and access point, there are also a number of physical capabilities of the client itself that we need to consider when we're trying to determine just how fast a client can connect to the network. The first thing we might like to think about is the band support of the client. We've got two bands to choose from. We've got the 2.4 gigahertz and the 5 gigahertz bands that the client may support. Most modern clients will tend to support both bands, but you do get older clients which still only operate on 2.4 gigahertz, and depending on which band we support and we use with the client, that gives us a number of other options in terms of other features with regard to 802.11 amendment features that we can actually use. So we've got the band support is the first thing. The next thing I want to talk about is the number of streams and antennas that the client will actually support. And we're going to dive into this a little bit more deeply very shortly. But briefly, with the advent of 802.11n, we had the emergence of a new concept within wireless LAN networking, and this is the concept of spatial streams. And this is actually a mechanism which allows us to transmit multiple RF signals at the same time between a client and a wireless access point. So if a client can transmit 2 streams, this will actually double the speed that we can achieve with that client. If it will transmit 3 streams, that actually triples the speed. So as I say, this is something we'll dive into a little bit more deeply in a moment, but certainly the number of streams and related to that the number of antennas that our client has will certainly determine the speed that we can connect at. Another factor is the channel width that a client will support. support if we can actually start to bond channels together, which we've spoken about previously. We can multiply up from base 20 megahertz channel up to 40 and 80 megahertz channels. With wider channels, we can again get some speed improvements. And of course, the 802.11 amendment support that the client has will very much determine which of these features can be used and which speeds can be achieved. For instance, an 802.11n capable client has access to a lot more capabilities than an 802.11a client, which is one of the older 802.11 amendments. And similarly, if we think about an 802.11ac client, it can certainly potentially support higher speeds than an 802.11n or 802.11a amendment supporting client. So it's very much the case that we have to consider all of these factors when we're trying to get some idea of the speeds we might achieve from a wireless LAN client. It's not simply the case that if we buy an 802.11ac capable client, we're going to be able to get a 1.3 gigabit connection between our wireless LAN clients and wireless access point. There are all of these different physical and environmental factors that we need to factor in so that we can understand the realistic speed that a client might connect to our wireless LAN network. So we're just going to take a few moments now to delve into the concepts of streams and channel widths, which I mentioned previously. If you're actually following along with the slide presentation, we're actually at slide number 32 now, and on slides 32 and 33, there are a couple of very useful graphics that you might want to have a look at to follow along with the explanation I'm going to give you now. It will actually make quite a bit more sense if you have access to view the slides. So going back in the mists of time, back to the 802.11b, 802.11g and 802.11a amendments, in the good old days, we only had the concept of single input, single output. This is also known by the acronym Siso, single input, single output. And back in the good old days, all we had was a single RF signal traveling between a wireless LAN client and our access point. And so this meant we had a single stream of RF data traveling between the client and access point. And this was the standard mode of operation for wireless LAN networks for many years. In previous episodes, we've also talked about the basic channel width, which is used by wireless LAN networks. We described how a 20 megahertz channel width is the basic width which is used, and this was used by the older legacy amendments, so 802.11a, b, and g. And it was certainly the case in the older amendments that only a single channel would be occupied by a client and an access point at any point in time. So thinking about the 2.4 gigahertz network, it would likely be channel 1, channel 6 or channel 11. And thinking about 5 gigahertz, we'd be looking at channel 36 or maybe channel 40, channel 44. But the point is the client and the access point would only be occupying a single 20 megahertz channel. So this is how things ran on the older legacy amendments until we got up to 802.11n. 802.11n represented quite a seismic shift in terms of client speeds for wireless LAN networks. So with the arrival of 802.11n, we actually moved away from the concept of a single input, single output with a single data stream between a client and access point, and we actually moved to the concept of multiple spatial streams. It was a technique called MIMO, which is multiple input, multiple output. And this meant that we could have multiple simultaneous streams of data flowing between a wireless client and a wireless access point. In the early versions of 802.11n equipment, we had two spatial streams, and this doubled the speed that we could achieve between a client and an access point. And then later on, with the second wave of equipment that came along that supported the 802.11n amendment, we actually moved up to three spatial streams, which actually tripled the speed that a client could achieve compared to a single stream Siso client. The thing to bear in mind here is that in order for these speeds to be achieved, to use two or three multiple spatial streams, both the client and the wireless access point both had to support the same number of streams. So if we wanted to use 2 streams on the wireless LAN client, our access point had to be able to support 2 streams. And similarly, if we wanted to use 3 streams and get triple the speed, the access point also needed to be able to support 3 spatial streams. And the number of spatial streams supported is also directly related to the number of antennas. We have to have 1 antenna per spatial stream. So if we're supporting 3 spatial streams, our client and our wireless access point must have 3 antennas to transport the 3 simultaneous streams. So if you're actually following along with the slide deck, on slide number 32, at the top there you can see we've got a legacy client, an 802.11a client, which is using Siso technology, single input, single output. There's a single stream of RF data between the client and the wireless access point. And then when we moved on to 802.11n, we've actually got 2 streams of simultaneous data, which is traveling via 2 antennas between the access point and the wireless LAN client, and this doubles our speed. In fact, it more than doubles the speed which we achieved with the legacy standards. We also had improvements to things like the data encoding techniques at 802.11n, so this is why we could more than double the speeds that we could previously achieve with the legacy amendments. In addition to the concept of multiple spatial streams, which 802.11n introduced for us, we also had the introduction of the concept of channel bonding. So this meant that we could take our basic 20 megahertz channel and actually bond it together with an adjacent channel and give ourselves a 40 megahertz channel width. So this would give us double the channel width which we'd previously been able to achieve with the legacy amendment clients. So when we went from 20 megahertz channels to 40 megahertz channels, we could actually double the speed that we were achieving between the client and the access point. In order to be able to bond channels together, they actually had to be next to each other in the radio frequency spectrum. So for instance, we could bond together channel 36 and 40 to give us a 40 megahertz channel on the 5 gigahertz band, or we could bond together maybe channels 44 and 48, but they had to be bonded together in adjacent channel pairs to give us this doubling of throughput. And again, in order to be able to take advantage of the 40 megahertz channel bonding and to double the speeds, both the wireless LAN client and the wireless access point had to support the 802.11n standard to be able to take advantage of this increased channel width and the resulting increased speeds. So if you're following along with the slide deck, we're actually on slide number 33 now. And at the top there, you can actually see we've got an 802.11n client, which is using a 40 megahertz channel to talk to an 802.11n wireless access point. And as we've previously stated, this more than doubled the speeds that we were able to achieve with the legacy amendments. But we must remember that this relied on both the wireless LAN client and the wireless LAN access point both being able to support the 802.11n standard and to be able to support 40 megahertz channel bonding. If we actually move to the bottom of that particular slide, so say slide number 33 in the slide deck, we actually take the concept one stage further. So with 40 megahertz channel bonding, we managed to double our speeds, and we've previously spoken about the concept of MIMO. We've got multiple input, multiple output, so we've got multiple streams at the same time. If we actually combine the 40 megahertz channel bonding, which gives us a doubling effect in terms of connection speed, and then we actually combine that with multiple spatial streams, we can actually increase the connection speed further. So we can use 40 megahertz channel width to double the speed. Then if we use 2 spatial streams between the access point and the wireless LAN clients, we can double it again. So this combining of the channel bonding and the multiple input, multiple output technique gave us some fairly significant increases over the legacy amendments which we'd used previously, and we were certainly well up into the 300 megabits per second connection speed territory when we were running with 40 megahertz channels and 2 spatial streams. And later on, when we actually moved up to 3 spatial stream support for clients and for wireless access points with the second wave of 802.11n equipment, we were getting up to 450 megabits per second connection speeds, which was way in excess of anything we've been able to achieve previously with the legacy amendment support. It's also worth mentioning that the Gigabit Wireless LAN amendment 802.11ac also uses and builds upon the same techniques as 802.11n. With 802.11ac, we can use 20 megahertz, 40 megahertz, and even 80 megahertz channels now if we have sufficient spectrum available. So that gives us another speed increase again. And again, 802.11ac uses MIMO technology. Much of the latest 802.11ac equipment will use 1, 2, or 3 spatial streams, but there are new devices in the pipeline which will use 4 spatial streams, which will give us another increase in connectivity for wireless LAN devices. But again, we need to remember that the wireless LAN clients and the wireless LAN access points that they're connecting to both have to be able to support all of these features to enable both the client and the wireless access point to support them. When there is a disparity in the features supported between a wireless LAN client and the wireless LAN access point, then obviously the lowest common denominator applies in terms of the channel widths and the number of streams which are supported. We've taken a look at quite a few factors now which influence the speed at which a wireless LAN client will connect to a wireless LAN network. And it's worth emphasising some of the key takeaways that we've actually covered. We need to remember that the speed at which a client will connect is not purely related to the capabilities of the wireless LAN infrastructure that it's connecting to. If we have wireless LAN access points which all supports 802.11ac, we can't expect our clients to connect at 802.11ac gigabit speeds. It's very much dependent on the capabilities of the client itself as well. If the client itself can't support the 802.11ac amendment, then it's simply not going to connect at these higher speeds. The client speeds and capabilities must match with the wireless LAN infrastructure itself. And conversely, if we've got clients that support higher level 802.11 amendments, for instance, if we buy 802.11ac clients, if we've only got a wireless LAN infrastructure consisting of 802.11n access points, we're simply never going to achieve the 802.11ac speeds that our clients are capable of until we upgrade our wireless LAN infrastructure to support 802.11ac. There's one further caveat that we need to bear in mind when we're thinking about wireless LAN client speeds. Even if we have a match in terms of the 802.11 amendments between our wireless LAN clients and our wireless LAN access points, this doesn't necessarily mean that the wireless LAN clients are going to run at the full published speed of the 802.11 amendment. For instance, if we have 802.11ac clients talking to an 802.11ac wireless access point, this doesn't mean that we're actually going to achieve the full advertised speed of 1.3 gigabits per second for the 802.11ac amendment. The reason for this is that clients, even though they support 802.11ac, they will vary in terms of which elements of the amendment they support. Not all amendment specifications are mandatory, and they just may not have the physical capabilities to be able to support all aspects of the amendment. For instance, many smartphones which may support 802.11ac can only support one spatial stream. Because of power limitations, because they're a battery operated device, they can't actually supply the power budget required to support 2 or 3 spatial streams, so they can only support a single spatial stream. So even though we may have a wireless access point, which is a 3-stream 802.11ac access point, we're just connecting single stream wireless LAN clients to that particular access point, and so the lowest common denominator there is going to be the single stream of the wireless LAN client. So if we've got a single stream client talking to a 3-stream wireless access point, the client is never going to be able to use more than that single stream, so that limits the speeds which it can achieve. And similarly, we also need to bear in mind the configuration of our wireless LAN infrastructure. Although 802.11ac clients may be able to operate on 20, 40 and up to 80 megahertz channel widths to give us the extra speeds which 80 megahertz would provide for us, it may well be that the wireless LAN infrastructure isn't configured to support 80 megahertz channels. 80 megahertz channels actually consume quite a big chunk of frequency spectrum, and in many countries it isn't actually feasible to use 80 megahertz channels as yet. So it may be that the wireless LAN infrastructure is only configured to support 20 or 40 megahertz channels, so it may well be that the client connectivity speed is limited by the wireless LAN infrastructure itself. So just to summarize this realistically, we need to think about the capabilities of our wireless client. We need to think about the capabilities of our wireless LAN infrastructure, and it's always going to be the lowest common denominator which is going to apply in terms of the connectivity speed which is achieved. So for instance, if we have an 802.11ac client connecting to an old 802.11a access point, then we're never going to be able to achieve anything more than the 54 megabits per second that we were able to achieve at 802.11a. And conversely, if we have an 802.11a client connecting to our latest and greatest 802.11ac access point, it is going to be limited by the fact that it can't connect beyond the limitations of the 802.11a amendment, which means it's limited to 54 megabits per second, even though the access point it's connecting to would enable a sufficiently capable client to connect at higher speeds of maybe up to 1.3 gigabits per second. So it's really key to remember that we need to understand the capabilities of our infrastructure and understand the clients which are going to connect to the infrastructure to understand exactly what sort of connection speeds they're going to be able to achieve, and that we're actually going to be able to supply to our end users in terms of the end user experience. So that pretty much wraps it up for this particular episode of the podcast. Don't forget, if you'd like to review any of the supporting materials, such as the slides and other audio presentations that I've done previously, you can get along to the website, which is wififorbeginners.com, and you can download everything for free there. And we've got some quizzes as well as some other resources you might like to check out as part of your wireless LAN studies. So just to recap what we've been talking about in this particular episode, we've been talking all about wireless LAN client speeds and what are the factors which determine the speed that a wireless LAN client will connect at. We started having a look at RF quality, what the factors are which determine the RF quality between a wireless LAN client and an access point. We talked about signal level, talked about errors, and we talked about noise, which can all affect the quality of the RF link between a client and access point. We then went on to look at some of the physical capabilities of a client which might affect the speeds it could achieve. We looked at band support, whether or not we're supporting 2.4 or 5 gigahertz or both. We looked at the number of streams and antennas that a client might support. We looked at channel width support, which is very important in terms of speeds we can achieve. And most importantly, we looked at 802.11 amendment support. The 802.11 amendment which a client will support will heavily influence the available connection speeds for that particular client. We then went on to look at Siso and Mimo. Siso is single input, single output. This is where we have a single stream of RF data passing between a wireless LAN client and a wireless access point. And then we looked at Mimo, which is multiple input, multiple output, which was introduced with the 802.11n amendment, which gave us the capability to transfer multiple streams of RF data to give us some fairly significant increases in connection speed. We then took a look at channel bonding. We talked about the fact that we can combine two basic 20 megahertz channels into a 40 megahertz channel. Again, this came along with 802.11n and gave us double connection speeds. And then we talked about combining both channel bonding and MIMO technology to give us even further increases in connectivity speed. And we also mentioned the fact that these techniques are used in the new 802.11ac amendment to give us even more increased connection speeds. We then spent some time just re-emphasizing the fact that we need to ensure that our client capabilities and our wireless LAN infrastructure capabilities match to ensure that we can achieve the full speeds that we expect from our clients. We We need to understand the capabilities of our clients. Even though they may support a particular 802.11 amendment, they may not support all facets of that amendment and may have some limitations in terms of feature support. We also need to understand how our wireless LAN infrastructure is configured to see whether or not all features are in fact active, so that we can understand the speeds which are possible if we connect our client to that wireless LAN infrastructure. So that pretty much wraps it up for this particular episode of the podcast. I hope this information has been useful to you. Don't forget to get along to my website, which is wififorbeginners.com, where you can find out all the supporting information for the podcast. In the next episode, we'll continue our discussion of wireless LAN clients and wireless LAN client capabilities. So look forward to joining you again soon on the next edition of the Wi-Fi for Beginners podcast.